Hello and welcome to another exciting instalment in the vibration series of lecture presentations. This is now part 3. In part 1 of the lecture series, we introduced some basic terminology, notation and general knowledge related to vibration and damping analysis. In part 2, we developed this knowledge and consider an analytical approach to calculating the amplitude and phase angle for damped spring mass systems subject to an applied external disturbing force. And this part 3 of the presentation, we're now going to use the formula derived in part 2 to actually undertake some practical questions associated with calculating amplitudes, symbol A, and phase angles, symbol phi. It's strongly recommended that you've overviewed parts 1 and parts 2 of this lecture series before considering the contents of this part 3. Here's a brief overview of the contents of this part 3 of the lecture series presentation for vibrations and damping. Initially, this presentation commences with a brief recap of the nomenclature used and the formula derived from the previous presentations. We then work through in detail example 1a, which requires us to calculate the amplitude A and the phase angle phi for a damp mass spring system when subject to an applied external force. This example basically gives you a template for the solutions to the questions that follow. We then outline question 1a and question 2a. These questions essentially require the same solution to that for example 1a. Just extract the information carefully from questions 1a and 2a before attempting the solutions. Be careful of units and prefixes, etc. In question 3a, we'll actually be given the amplitude in the question, but we'll now need to calculate the damping force Fd. So that requires some transposition. In question 4a, we've got to calculate the damping constant C, again requiring some transposition of the equations. And question 5a, we've got to calculate the angular velocity omega of our rotating mass. That will actually require to generate a quadratic equation and solve using the quadratic formula. Just note for your reference that the presentation contains solutions to all questions except for question 4a. That solution is left for you to develop on your own. The overview continued. Here are the approximate start times for the various sections within the presentation to hopefully aid your access through the presentation, but please note they are only approximate start times. I will state on the next few slides the summary of nomenclature and formulae that were used in the previous presentation. This is the first slide defining some terms, for example the main mass of the system or the mass of the machine is capital M and the rotating or offset mass is lowercase m, so be careful of your notation used. Notice all masses must be used in kilograms. And displacement, symbol x in meters, and the amplitude, which is the maximum value of x, symbol A, also in meters. Here are various equations that were derived previously. The numbers used to define the equations are quite arbitrary, but I would encourage you to familiarize yourself with the terminology, notation, and the formula here. The summary continued here. Just recap some basic damping terminology and characteristics here. Also be careful of the terminology. These are angular velocities associated with the rotating offset mass, lowercase m here, in RPM in radians per second. We also refer to the undamped natural frequency, omega n, and then the damped circular frequency, omega d. Summary continued. Here are a formula for calculating the amplitude squared of our system and calculating the phase angle, angle phi, and also the formulae for the maximum forces related to spring force, damping force, and inertia force. So that's a very brief recap of some of the information from the previous presentation. Let's consider an example. Here's example 1a. The diagram on the right hand side shows a mass spring dashbox system to which a harmonic disturbing force is applied, which is defined by the equation F is equal to 400 multiplied by the cos of 30t newtons. We're asked to calculate the amplitude of the mass, the main mass shown here, and the phase angle. Given the spring stiffness K is 10 kilonewtons per meter, the main mass M is 5 kilograms, and the damping constant C is 150 newton seconds per meter. The answers are given in the bracket here. And essentially we'll be using equation 11 and 12 to solve this particular solution. The first thing, as always, is to read the question carefully and extract the information from the question. So example 1a, here's the work solution. The spring stiffness K is 10 kilonewtons per meter, so that's 10 times 10 to the 3 newtons per meter. The main mass, capital M, is 5 kilograms. M is 5 kilograms. The damping constant C, 150 newton seconds per meter. C, I've written that as 150 newton per meter per second. It's the same unit, it's written a different way. And notice that the force is stated as 400 multiplied by the cos of 30t newtons. So extracting the information from the question, we can clearly see that F0 is 400, so F0 is 400 newtons. And we can see that omega is 30, so the angular velocity omega is 30 radians per second. Just note for reference that this omega value is the angular velocity of the rotating mass, lowercase m. So that's implicitly given in the formula for the disturbing force F. Now we can calculate the undamped angular velocity, omega n, which we'll need for our equations. That's the square root of k divided by m. So we have the value of k from above, we have the value of m from above. So we can determine the value of omega n. In this case it's 44.72 radians per second. Next we can calculate the critical damping constant Cc. That's 2 multiplied by the square root of mk. So that's 2 multiplied by the square root of. We have the main mass from above, and we have the spring stiffness K from above. So Cc evaluates to 447.21 newtons per meter per second. Our damping ratio zeta is the damping constant C divided by the critical damping constant. So our damping constant C above is 150. We just calculated the critical damping constant. So the damping ratio zeta is 0.335. I just note from our previous work, as the damping ratio zeta is less than 1, it's classified as underdamped. In other words, it allows vibrations to occur. That's extracting the information from the question and calculating various parameters it will need to solve for the amplitude and the phase angle phi. Example 1a, the solution continued. So now we can calculate the value of a squared using the formula derived previously. The equation shown here, 11b. We insert the appropriate values into the equation. Notice with this format of the equation, the bracketed term here is raised to the power of negative when we're actually dividing by that bracket. Just be careful of how you use that in your calculator. But a squared evaluates to 0.00317. Of course, we really want to find amplitude A, so square rooting both sides. That's 0.056 meters or 56 millimeters. Now we're going to find angle phi. So using the equation tan phi is equal to this expression. And that's equation 12 on our summary slide, which is written on one line here, that's all. And again, inserting the values, notice they were actually calculated up here. So we can just use these values for ease of reference. So that gave us a value for tan phi of 0.8172, And again, we need to find the angle, so we're going to take the inverse tan of both sides of the equation, so inverse tan of the ratio, so 39.26 degrees. Because we've got a positive tan ratio, that puts us in this first quadrant here for the value of angle phi on our ASTC diagram. Of course, from the ASTC diagram, there is actually a second solution for a positive tangent ratio in the third quadrant here, which would be 180 degrees plus angle 39.26 degrees. But in this case, I've only stated the first solution from the first quadrant. So here are some tutorial questions related to calculating the amplitude and phase angle. It's question 1A. I'll let you read the question carefully, very similar to example 1A in its format. We have to calculate the amplitude of the main mass and the phase angle. Answers are shown in the bracket here. And question 2A, again very similar to its format. And again we have to calculate the amplitude and the phase angle. Again the answer shown in the bracket. I would encourage you to stop the presentation and attempt questions 1A and 2A. The solution sequence are quite similar to that we used for example 1A, so you can use example 1A as a template. Just make sure you read the questions carefully, extract the information appropriately, be careful with units and prefixes, etc. Particularly regards question 2A here, the machine's mass is stated in terms of tons. And notice that the spring stiffness and the damping coefficient or the damping constant, these values include prefixes, so account for those. But as I say, solution is very similar to example 1A. The main objective of these questions is to try and make you familiar with the solution process, the various values, units, notation, and formulae involved with finding the amplitudes and the phase angles. I will briefly overview the full work solutions on the following slides. Here's question 1A, solution. This is very similar to example 1A, so I'm going to let you review the solution at your own pace. It's essentially the same procedure, just with different numbers. Ensure you extract the information from the question carefully. Just again note that omega is obtained from the original disturbing force equation. And the disturbing force F is equal to 200 multiplied by cos of 30t. Remember that's of the form F is equal to F0 cos omega t. So the 30 is omega. So our angular velocity of the rotating mass, lowercase m, is 30 radians per second. And the force F0 is 200 newtons, shown here. So we're evaluating for the amplitude, it's 16.2 millimeters. And be careful when working out the phase angle phi from our equation here. That evaluates to be a negative ratio in the second quadrant and in the fourth quadrant. So when we calculate the angle alpha here, note for reference, this is angle alpha. We have to subtract that from 180 degrees to find phi. So phi is 180 minus the alpha. And that evaluates to 103.1 degrees, stated to one decimal place, as was the answer in the original question. And that's shown here. A note from our ASTC diagram, there's actually a second angle in the fourth quadrant, but it's usually the first angle stated in the solution. Question 2A, solution. Again, very similar to the previous question. Just be careful here when you extract the information from the question. You note the units used. For example, the machine's mass is 0.15 ton. So capital M here is 150 kilograms. The stiffness of the base is stated as 60 kilonewtons per meter. So account for the prefix there. Lowercase k here is 60,000 newtons per meter. And the damping coefficient or the damping constant is 5 kilonewton seconds per meter. So damping constant C here, that's 5,000 newton seconds per meter. The harmonic disturbing force F is stated here as 800 cos 25t. So again, that's in the format of F is equal to F0 cos omega t. So the F0 in this case is 800 newtons and the omega is 25 radians per second. Same solution sequence as before. Calculating the amplitude, it's 6.18 millimeters. I think the answer stated in the original question was to 1 decimal place. And again, be careful calculating the angle phi. First of all, I'm going to calculate angle alpha. Here's angle alpha. Angle alpha calculates to be negative 74.88 degrees. Note we're in the negative quadrant for tangent ratio on our ASTC diagram. So to actually calculate angle phi, the phase angle, it'll be 180 degrees minus angle alpha. So 180 degrees minus our 74.88. So phi in this case is 105.1 degrees. And that's stated to 1 decimal place, as was the answer stated in the original question. Mathematically, there is a second solution for a negative tangent ratio in the force quadrant, but it's the first solution we usually specify in our answer. Here's question 3a. A load of 1.2 tons resides on a support having a stiffness of 900 newtons per centimetre. There is a damper positioned between the load and the support having a damping coefficient of 7.5 megagrams per second. The system is subjected to an applied harmonic disturbing force F is equal to F0 cos 5t newtons. If the amplitude of vibration is to be limited to 1.2 centimeters, we're asked to determine the maximum magnitude of force F0 which can be applied to the system. I would encourage you to start the presentation and attempt question 3a, but the full work solution is overviewed on the following slide. Question 3a, here's the solution. Again, ensure you extract the information from the question carefully. Our load in this case, or our main mass, capital M, it's 1.2 tons, so that's 1200 kilograms. Be careful, the support stiffness is 900 newtons per centimetre, so K is actually 90 newtons per millimetre, so that's 90,000 newtons per metre. Again, you might want to use a unity bracket to help structure these conversions. Sometimes students do have problems with such conversions, so our cancelling unity brackets offer a structure for the conversion. Just for reference, here's our unity bracket calculation. We're converting 900 newtons per centimetre into newtons per metre. So this is the unity bracket. And remember, it's a cancelling unity bracket. So in this case, in our unity bracket, the 100 centimetres is written in the numerator because we have to cancel the centimetres. So we are left with the unit of the newton per metre for our spring stiffness. So 900 newtons per centimetre converts to 90 kilonewtons per metre. If you require further information, there is a separate presentation on unity brackets. The damping coefficient or damping constant is specified in terms of megagrams per second, so C 7.5 megagrams per second is actually 7,500 newtons per metre per second. Remember that damping constant or damping coefficient can be stated in various units. On this particular question, we're actually given the amplitude of the vibration. It's actually limited to 1.2 centimetres. So amplitude capital A is 1.2 centimetres, which converts to 0.012 metres. The question states the disturbing force, capital F here, that's in the format of F0 cos omega t. In this particular question, it's F0 we are trying to find, so that's an unknown. But our omega in this case will be 5, so omega is 5 radians per second. So as with the previous questions, we calculate our undamped angular frequency, our critical damping constant and our damping ratio, all parameters we need to determine within the solution. Again, we're using the same equation as we have in the previous questions related to the amplitude squared, but this time the unknown is the F0, the maximum disturbing force. So we need to rearrange the equation to find F0. I'll let you review the transposition at your own pace, but F0 evaluates to 849 newtons. Question 4a. A machine tool's main body has a mass of 0.85 megagrams and is supported on mountings of stiffness 75 newtons per millimeter. A damper is to be designed to sit between the main body and the support. If the machine is subjected to an applied harmonic disturbing force, F is equal to 500 cos 6t newtons, and the vibration's amplitude is limited to 8 millimeters, we have to calculate the damping constant required. That's usually symbol C in our nomenclature. The damping constant is 7,333 kilograms per second. I will leave you with question 4 and let you develop the solution for yourself. It follows a similar approach to the previous questions, but this time you're trying to calculate damping constant C. In question 5a, a mechanical system has a main mass of 216 kilograms, resides on a base having a spring stiffness of 120 newtons per centimeter. A damper sits between the system and the base and has a damping constant of 2,800 kilograms per second. If the machine is subjected to an applied harmonic disturbing force, F is equal to 850 multiplied by cos omega t in newtons, and the vibration's amplitude is limited to 1 millimeter, we've got to calculate the rotational velocity omega, given the above information. There's a hint in the question here. From the information, we've got to generate an equation in terms of omega to the power of 4. We then use a substitution that x is equal to omega squared. This will then form a quadratic equation in x. We solve the quadratic equation for x, and then we can back substitute to find the value of omega. Essentially, if we apply the process we have in the previous questions, using our equation 11, we insert the values, we will generate an equation including omega to the power of 4, then using the above substitution, we'll be able to form a quadratic which we can solve using the quadratic formula. Here's the quadratic formula for reference. I would encourage you to start the presentation and attempt question 5a. It is more complicated with regards to the mathematical manipulation to form the quadratic equation and of course then to solve it. But the initial part of the process starts off in the same way as the previous questions we've considered. I'll overview the full work solution on the following slides. Here's question 5a, the beginning of the solution. I will let you review this at your own pace, but as always we need to extract the information from the question first of all, and in this question we have to calculate the rotational velocity of the system. That's the value of omega. That is the angular velocity of the rotating mass, the unknown here. As with all the previous questions we considered, we use this equation from our notes related to amplitude squared, which we labelled as equation 11 for reference. If you now insert the values from the question into the equation 11, you will find that we will form this equation. It contains an omega to the power of 4 term and an omega squared term. Notice I've generated this equation in terms of decimals. Some students I find generate the equation using third form, and that's absolutely fine and indeed more accurate, but my calculator didn't have that facility when developing this solution. So question 5a, solution continued. So continue with the development of the solution. So here's our simplified equation containing omega to the 4 and omega squared. And now, using the substitution hinted at in the question, we let x is equal to omega squared, and this will now form a quadratic in terms of x. So we solve the equation for x. Noting the values of a, b and c from the above equation, we can now solve for x using the quadratic formula here. Question 5a, solution continued. And of course, as always, when solving for a quadratic equation, there will be two solutions. And then noting the value of x is actually omega squared, we can find the angular velocity in terms of radians per second. And I've also stated the angular velocity in terms of RPM, approximately 597 RPM. So that's a full work solution for question 5a. Question 5a solution is a check we can undertake to confirm our final answer. If you now substitute the value of omega calculated on the previous slide into equation 11, in other words inserted here and here, you can then check if the answer calculated for omega is correct. In other words, if the left hand side of the equation is the same value as the right hand side of the equation. But that's just for reference. And finally, for your further reference, I'll just show you this solution for question 5a. Thanks to Polly Watson for allowing us to see her solution. Polly has used the third form throughout her submission, shown here, which avoids the potential for rounding errors to occur and thus can result in a more accurate final answer. So I'd encourage you, where possible, instead of using the decimal values, as I tendency to do, preferably use fractions or surd values if your calculator displays answers in such formats. Here's the bibliography used to help generate the presentation. This concludes part 3 of the presentation related to the vibration and damping lecture series. If you still have the will, there's one more presentation to review, which contains slightly more complicated questions. Hope to see you for part 4. Thank you for viewing.